Hello, everybody. Let's see you again. And let's start our lecture today. Okay, it's lecture number 2. And just I want to open my presentation clip. And so let's go. Choosing a proper sensor is certainly not a trivial task, believe me. First of all, the task that is to be supported by one or more sensors needs to be thoroughly analyzed and all possible strategies to be reviewed. Potential sensors should be precisely specified, including environmental conditions and mechanical and also electrical constraints. If commercial sensors can be found that satisfy the requirement, purchase is recommended. Special attention should be given to interface electronics in general, available as separate units, but rarely adequate for newly developed mechatronic systems. So, if the market does not offer the right sensor system, such a system may be assembled from commercial sensor components and electronics. In this lecture, give some physical background of most sensors to help understand their operation, to assist in making a justified choice, or to provide knowledge for assembling particular sensing systems. So, sensor selection is based on satisfying a requirement. However, these requirements are often not known precisely or in detail. In particular, when the designer of the system and its user are different persons. And in real engineering job, in company, in some big industries, it's so important. So the first task of the designer, therefore, is to get as much information as possible about the future application of the system, all possible conditions of operation, the environmental factors, and the specification with respect to quality, physical dimensions, and certainly, of course, the list of demands should be exhaustive. Even when not all items are relevant, they must be indicated as much. This will leave more room to the designer and minimizes the risk of having to start all over again. The list should be made in a way that enables unambiguous comparison with the final specification of the design system. Once the designer has a complete idea about the future use of the system, the phase of the conceptual design can start. Okay? Before thinking about sensors, the measurement principle first has to be considered. For the instrumentation of each measurement principle, the designer has a multitude of sensing methods at his disposal. For the realization of particular sensor method, the designer has to choose the optimal sensor component and sensor types from a vast collection of sensors offered by numerous sensor manufacturers of our planet. This design process is illustrated by an example of a measurement for just a single static quantity. We have the amount of fluid in a container. For instance, we have a drink dispenser. Okay? The first question to be answered is, in what unit the amount should be expressed, volume or mass? This might influence the final selection of the sensor. So, this figure shows various measurement principles in a schematic way. A, as you can see, the tank is placed on a balance to measure its total weight. B, a pressure gauge on the bottom of the tank. C, you can see this. It's a gauging rule from top to bottom of the tank. C is this one, and D in this bottom, the level detector on the bottom, measuring the column height. E, here in this part, the level detector from the top of the tank, measuring the height of the empty part. And F, mass or volume flow meter at both inlet and outlet. Okay? Obviously, many more principles can be found to measure a quantity that is related to the amount of fluid in our reservoir. In the conceptual phase of the design, as many principles as possible should be considered, even unconventional ones. Based on the list of demands, it should be possible to find a proper candidate principle from that list, or at least to delete many of the principles for an argued base. For instance, if the tank contains a corrosive fluid, a non-contact measurement principle, in this case, is preferred, right? Putting principles B, C, and G, here we can see here B, C, and D on a lower position in the list. And further, for very large tanks, method A, in this case, can be possibly be eliminated because of its high cost, right? The conceptual design ends up with a set of principles with pros and cons, ranked according to the prospect of success. After having specified a list of candidate principles, the next step is to find a suitable sensing method for each of them. In the examples of this slide, we will further investigate the principle E. The principle E here on the top, a level detector that placed at the top of our tank. It should be noted that from level alone, the amount of liquid cannot be determined. The shape of the container should also be taken into account, right? Again, a list of various possible sensor method is made as follows. So, E1, it's maybe a float connected to an electronic readout system. E2 may be optical TOF measurement. E3, optical range measurement. E4, electromagnetic distance measurement for radar. And E5, acoustic TOF measurement, and so on. As in the conceptual phase, these methods are evaluated using the list of demands. So not only the characteristics of the sensing method, but also the properties of the measurement object, like kind of liquid and shape of tank, and the environment should be taken into account too. For the tank system, the acoustic TOF method time of flight could be an excellent candidate because of its being contact-free. In this phase, it is also important to consider method to reduce such environmental factors as temperature. Ultimately, this phase concludes with a list of candidates sensing methods and their merit and demerit with respect to the requirement. The final step is the selection of the components that make up the sensing system. Here, a decision must be made between the purchase of a commercially available system and the development of a dedicated system. The major criteria, first of all, are cost and time. Both are often underestimated when developed by one's own inconsiderate. So, in this phase of the selection process, sensor specifications become important. Sensor provides published specifications in datasheets or on the internet. However, the accessibility of such data is still poor, making this part of selection process critical and time-consuming, in particular for non-specialists in the sensor field. Evidently, the example of the level sensor is highly simplified, whereas the selection process is usually not that straightforward. Since the sensor is often just one element in the design of a complex mechatronic system, close and frequent interaction with other design disciplines, as well as the customer, in this case, recommended. Sensors play a critical role in a current developments in industry and the Internet of Things. They are more often than not referred to not just as the transducers converting physical signals to the electrical domain, but are discussed as a complete system. A sensor node in Industry 4 or in the Internet of Things normally consists of an embedded integrated system containing power, processing, means of communication, and eventually the sensing element. Large amount of data, or big data, are generated using vast networks of smart sensor nodes measuring plant conditions, water quality, or the weather, often with greater robustness, higher accuracy, or better resolution than conventional remote sensing technology has. This means that for smart industry, Internet of Things and mechatronics applications, the possibility for interfacing and embedding processing of sensor signals are almost as important in the selection criteria as the choice of a suitable physical transducer. To underline this importance, for every physical principle, a number of embedded processes examples will be discussed. These are by no means meant as design guidelines or full-blown recipes, but aim to give insight in the possibilities, offer an option for learning, and can be used as starting point for further design or development. The sensors discussed in this our lecture are mainly transducers translating quantities in a physical domain into electrical domain. As you remember, I mentioned this in previous lecture. The discussed applications, namely in mechatronics, are largely not only in the electrical signal domain, but in the digital domain as well. A transducer converts or transforms information, or thus power, from one domain into other. Also, the act of absorbing changes the observed, though not only true in quantum mechanics. In ideal, transducer converts as little energy as possible in order not to have an impact on the measurer. This means that the converted electrical measurement signals are typically small and need additional conditioning such as amplification, offset reduction, and linearization. And this can be achieved in many ways: by clever sensor design, by adding conditioning security, or by processing the data in the digital domain. For processing data in the digital domain, it is necessary that data have been converted from one electrical domain in a digital representation, typically by analog to digital conversion. Alternatively, sensors can also be designed in such a fashion that their primary output is already in the digital domain. It may be incremental encoder or especially absolute optical encoders give the output in digital, you remember, step or bits. This approach, schematically shown in this slide, can be recognized in most of the common or household digital sensing systems, such as digital pivot thermometers or bathroom scale. Okay? The circuits for conditioning, conversion, and processing are usually condensed to a single integrated circuit, usually outputting data on a small liquid crystal display. For every type of transducer, a number of strategies for interfacing accompanied by useful conditioning circuits exist. So, when eventually a voltage is generated that has a linear relation, is preferable for us, or at least changes with the measurement. And the board in the electrical domain can be considered count. And the signal can be converted to the digital domain, typically with ADC. Okay? For further processing, and finally visualization and interpretation. In order to illustrate the interfacing options and simple processing algorithms, a platform has been chosen which has become a de facto standard in education and do-it-yourself DIY application. In this case, the Arduino platform has been built around a number of members of HTML AVR RISC reduced instruction set 8-bit microcontroller series. In recent years, the family has been expanded to boards based on ARM, namely Intel x86 architecture, and many, many more. Yeah, they're growing so rapidly in all parts of the planet. While there exist many more systems embedding architecture, families, boards, etc., this choice has been made in the hope to provide accessible and reproducible examples which can be easily translated to a different system of choice. The board, which will be used for experiments and examples discussed in the most common member of Arduino family, is Arduino Uno. Look at this figure, please, which has been in development for more than 10 years and not sustainably changed, merely fine-tuned in the process. So this board consists of an ATmega 328P microcontroller by Atmel running at 16 MHz. It's a small power section, linear 5 and 3.3 volt regulator, and a separate ATmega 8U2 microcontroller, which is used as USB CDC device for programming and communication. A single USB connection can be used for both programming the device, like uploading new programs into the main controller flash memory, and communication with the device. Many more boards exist in the Arduino family, using a large variety of communication and programming protocols, such as JTAG or one-wire debug, native USB, and communication protocols such as Bluetooth, Wi-Fi, LoRaWAN, etc. But these are also interesting for developing sensor nodes and network circuits, considered beyond the scope of our understanding the basics necessary for embedding processing. So a number of publications are referenced to act as starting points for more elaborate development. The ATmega 328P controller, which forms the heart of the discussed Arduino board, is our 8-bit RISC microcontroller running at the same 16 megahertz. The risk implies that most of the low-level instructions can actually be processed in one clock cycle. This means about 16 million instructions per second. The controller has 4 kilobytes of RAM memory, 32 kilobytes of flash memory for program storage, and 1 kilobyte of EEPROM. It contains a number of timers, which can be used for interrupts of the generation of pulse, with modulation signals and hardware support for a number of communication protocols. And certainly and standards too, like SPI, I2C, and a general purpose synchronous serial interface, like UART. For embedded sensing, one of the most relevant devices is the controller, is the ADC. The board that is used has a 6-channel 10-bit AD converter, which in the normal configuration, if you have single channel, can take a simple in 100 microseconds. What it means? It means a maximum sampling rate of 10 kilohertz, depending on how the sampling routine is configured and implemented. But you should note that this is largely caused by the implementation of the functions like analog read in the Arduino environment and library. It is possible to achieve higher sampling rates using different implementations in code, for example. The reference voltage for the internal AD converter can be set to an internal 1.1 volt reference, the default 5 volt supply reference for the external reference. Okay, so the input pins that can be used for AD conversion, the controller has just one AD converter and a 6-channel multiplex, and can be used as general purpose input or output pins as well. It is also possible to use an internal pull-up resistor on every input pin, and thus, in our simple cases, eliminated the needs for additional components for interfacing sensors. Software for the Arduino board can be written on an integrating development environment, IDE, integrated development environment. So IDE running on a host computer. Versions of this IDE exist for many operation systems, as Windows, as Linux, Mac, OS X, and can be downloaded freely. That's very advantage. And the source are licensed at GBS from Arduino. If you visited the Arduino.cc website, you may find. The IDE shown in this figure, in this slide, is written in Java and relies on the GNU AVR GCC compliant and AVR Dune project for respectively complying code in C++ and programming the device. In many applications for design and education, the input of a sensor is compared with a certain threshold value, and action is taken accordingly. Goal of the illustrated examples is to get a step further and translate the obtained sensor signal back to meaningful SI units. Is it okay? Let's now. The power of embedded control, even the relatively for computationally simple devices, as we have a 8-bit ADR microcontroller, has been shown by the development of the Maker DIY community of 3D printers, quadrocopters, and balancing vehicles. In real time, low-level sensing and control, maintaining the heart in a free heading and altitude of the quadricopter or the balance of a seatbelt. Even these examples carried out by the microcontroller, the overall, it means by human point of view, loop control by a host system or a remote operator. After interfacing, conditioning, and processing, the signals in the embedded platform, recording, visualization, and interpretation needs to take place as well, right? Okay, let's go on. Also, the Arduino IDE contains a number of tools for elementary visualization and recording of data. It's maybe serial monitor tool and a rudimentary graph writer, or a different tool is introduced here for recording, visualizing, and processing the sensor data on a host PC system. So, the platform used for a number of simple illustrating examples is aptly-named processing, freely obtainable for multiple operating systems. Usually you may do it from website of processing. You can see this website in right up corner, top corner, you might find this site. The IDEs for both processing and Arduino have a very similar look and feel. And this slide shows the IDE of processing with a graph right example. And you can see in the left part of this slide. They are by no means full-blown environment for industrial product development, but are specifically designed to create small tests, proof of concept, and working prototypes. Hence, programs are denoted as sketches. Much of the relevant information for getting started with embedded sensing, especially using the Arduino platform, can be found online. And this is very nice. A good starting point is Arduino's main website. In our lecture sequences, we first introduce a notation system for the quantities used in our lecture, and an ambiguous set of symbols for each quantity. So, a formal description of relations between quantities based on energy consideration is presented today, from which particular physical effects are derived, serving for specific groups of sensors that discuss a bit later. So, various frameworks developed for a system description of sensors are briefly explained. They are based on measurement, application field, Portal model, conversion principle, and energy domain. A sensor platform, the exchange of information, and hence the energy, right, from one domain to another. And as such, it operates as the interface between different physical domains. So I want to repeat, in this lecture, we first introduce a notation system for the quantities used here. Okay? So to avoid confusion with notation, we define unambiguous symbols for each quantity. For example, in the electrical domain, the symbol epsilon usually stands for dielectric constant, whereas it means strain in mechanical domain. And namely in this lecture, we use epsilon for dielectric constant only. A strain is denoted by capital S. So, several frameworks have been developed for a systematic description of sensors. Various approaches are presented, namely in today's lecture. Further, a formal description of relations between quantities based on energy considerations is introduced, from which particular physical effects are derived, sensing for specific groups of sensors that are discussed in our later lectures. Various attempts have been made to set up a consistent framework of quantity. Physical quantity can be derived into subgroups according to various criteria. And this leads to subgroups with different characteristics. Various attempts have been made to set up a consistent framework of quantity. Physical quantities can be divided into subgroups according to various criteria. This leads to subgroups with different characteristics, like with respect to direction, it may be quantity having a direction is called a vector, like velocity, right? A quantity that does not have a direction is a scalar, like temperature. And with respect to time behavior, it may be state variable describes a static property. It may be a rate variable that describes a dynamic property. Dynamic means that change during the time. Practically all technical engineering systems changes during the time. But during the some period of very short time, it may be seen it's static. So within one domain, state and rate variable are related as follows, as you can see the first formula of this slide on the top part of this slide. And with respect to energy, we may find that the quantity that is associated with an energetic phenomenon, often called a variable. It may be electric current or pressure. A quantity that is not associated with energy or only with latent energy, often called a material property, like length. Sometimes a property is also called a constant, but the value of most properties is not constant at all. So we will not use this term. It may be classified according with respect to dependency on mass of size. In this case, a quantity which is independent of the dimension or the amount of matter is called an intensity quantity. So intensive quantity. It's like temperature is an intensive variable and resistivity is an intensive property, right? Another, a quantity which depends on the amount of mass or volume, or maybe its expansion, and usually is called an extensive quantity, like charge is an extensive variable, and resistance is an extensive property too. So resistivity rho is a pure material property, whereas the resistance R depends on the material as well as the dimensions of the resistor body. In general, the relation between an intensive and extensive quantity within one domain is given by expression A equals G times A. So with A and G, general extensive and intensive quantities, and G is a geometrical parameter representing, for instance, the dimension of a sun. You know, in most cases, the value of a material properties is orientation dependent. This dependency is expressed by subscripts added to the symbol. Extensive variables are state variables. The time derivatives are rate variables or flow. Intensive variables are identical to effort. Flow and effort variables are discussed when conjugated pairs of variables are introduced. With respect to the endpoints of lumped element, we may now to explain this classification, we first introduce the term lumped element. A lumped element symbolizes a particular property of a physical component. That property is thought to be concentrated in that element between its two endpoints or nodes. Exchange of energy or information occurs only through these terminals. In this sense, we distinguish an cross variable defined by the difference of its value between the two terminals of a lumped element, like voltage and velocity, right? And a through variable, it's a type of variable that has the same value at both terminals of the lumped element, like electrical current and the force. Through variables are also called generalized I variables. A cross variable are called generalized V variables. However, this is just for the matter of viewpoint. It is preferably justified to call them generalized forces and displays. We will use these types of variables in a bit later, right? Okay. Various relations between quantities are discussed. Another classification with respect to cause and effect. In this case, output variables are related to input variables according to the physics of the system. Input variables can bring a system into a particular state, which is represented by its output variable. So, output variables depend on the input variable. Independent variables are applied from an external source to the system. And dependent variables are responses for the system to the input variable. Obviously, a variable can be dependent or independent according to its function in the system. For instance, the resistance value of resistor can be determined by applying a voltage across its terminal and measuring the current through the device, or just the other way around. So, in the former case, the voltage is the independent variable, and it is the dependent variable in the latter. The relation between independent and dependent variables is governed by physical effects, and certainly by material properties, or by a particular system level. In either act, within one physical domain or crosses domain boundaries. Such relations are the fundamental operation of science. Another classification with respect to power conjugation. Within a single energy domain, pairs of variables can be defined in such a way that their product is power, right? They are called power conjugated variables. And the members of such a pair are called effort variable and flow variable. And this table on this slide lists these variables from various domains. You should note that the dimension for each product is a power, right? And the magnetic quantity of current stems from the definition of magnetic field strength, where the number of amperes turned or magneto-motive force determines the field strength. Its power conjugate variable, in our case voltage, do you agree with me? Is actually the rate of change in magnetic flux with unit of Weber per second. Weber per second you see as a magnetic, here the line of the current A voltage, and this you can see unit Weber per second. But this is equal to the induction voltage. So we call this voltage. For practical reasons, the heat flow of W we have here is often taken as a thermal flow variable, rather than the entropy elated quantity, which is not measurable in a straightforward way. Yes, indeed. The domain is therefore sometimes called the pseudothermal. And you can see in the last in the bottom of this table. And this table summarizes various relations between rate, state, effort, and flow variables for the mechanical, electromechanical, magnetic, and thermal domain. Another rate of classification with respect to energy conjugation. Another way to define pairs of variables is based on the property that their product equals energy per unit volume. So we may see as J over meter. And this table lists their pairs for the major domain. The most fundamental categorization of quantities is based on thermodynamics law. The description is in particular useful in the field of material research and optimization of our sensor material. Derived from the thermodynamic approach is the bond-graph notation with a division of variables into effort and flow variables. You know, this method is not only useful for the description of sensors, but also has a great significance in the design of all kinds of technical systems, irrespective to the domain type. So, we repeat the list of pairs on the conjugate variables in this table together with their symbol. Mechanical translation in the first line, you can see its tension is a T Newton per square meter, and deformation S mechanical rotation. Electrical, you can see at another, its field strength E, and the electric displacement measured is C over M squared. Another line, magnetic induction, Weber per square meter, and magnetic field strength is this. And the last line is the temperature in kelvins usually, and entropy sigma. Okay? Comparing these pairs with the group from other categories given previously, we can make the following observation. The quantities E, D, B, H, T, and F are vector variables, whereas sigma and theta are scalars, therefore often denotes as delta sigma and delta theta, and that indicating the difference between two values. Moreover, if the above groups of quantities T, E, and theta are a cross variable. On the other hand, F, D, and sigma are through variables. And finally, you should notice that the dimension of the product of each domain pairs is always J over meter, J over meter, J over meter, energy per unit volume. Whereas the product of the pair effort and flow variables in this table has the dimensions of power, 1, right? So the energy content of an infinitely small volume of an elastic dielectric material changes by adding or extracting thermal energy and therefore exerting upon its electrical or mechanical force. If only through variables affect the energy content, the change can be written as follows, as you can see in this first equation on the top, on that part, this part. Whereas the disregard of the magnetic domain. Is it okay? Obviously, the cross variables in this equation can be expressed as the partial derivatives of energy. And we see the next 3 equations here. Likewise, if only across variables affect the energy content, the energy change is written as follows, and you can see this top equation. You may compare the difference between these ones. And The energy chain is written as this one. Here, the G is called the Gibbs potential. The through variable can be written as follows, and C adds another three equations in the right column. From this equation, we can derive the various material properties, but you shouldn't memory all of that. You should only understand the physical processes and why we use, namely, these relation between quantities. Okay, so we extend this equation only because the resulting parameters are more in agreement with experimental conditions like constant temperature, electrical field strength, and threat, as denoted by the script before. Is it okay? Okay, go. The variables S, D, and delta sigma are approximated by linear functions. So we can get these left column here, these three equations on the left part of our slide. Combining previous equations results in the right column. And so we can get another column. So now we have a set of equations, these 6 equations in this slide, with the independent across variables T, E, and theta. And the system configuration or the material couples are conjugate variables of each pair. The second order derivatives in the diagonal here, and you can see it represents the elasticity or compliance of material. It's actually called the Hooke's law. All other derivatives represent cross effect. So it's not for memorizing. It's only to more deep understanding its relation. Okay. So we should notice that these derivatives are pairwise equal things, assuming linear equation. The order of differentiation is not relevant, as we can see from these upper equations. So the derivatives in previous equation represent material properties. What it means? It means they have been given special symbol, right? And the variables denoting constancy are put as subscript to make place for the subscript denoting orientation. Usually it's all according to the logic. All our engineering job is the logic, physical. It's using the mathematical explanation. For instance, S is power, E, theta, is the compliance of constant electric field, E, and constant temperature, theta. Okay? The 9 associated effects are displayed in this table. What is 9? Electricity, direct piezoelectricity, piezo-caloric effect. In the middle, you have converse piezoelectricity, permittivity, electrocaloric effect, the same. And the right side of column, you can see the thermal expansion, pyroelectricity, and heat capacity. And these tables show the associated material properties. The parameters for just a single domain, like epsilon, Cp, and S here. The other parameters denote cross effect and describe the conversion from one domain to another. The piezoelectric parameters P, and you can see in this line, and D in a second line will be discussed in detail in the lecture on our piezoelectric number. Maybe we have separate lecture for this. So for now, note that direct piezoelectricity and converse piezoelectricity have the symbol G. Okay? Because the dimensions are equal, and you can see it's maybe meter per volt or C per amp. The same holds for the pure electricity and converse pyroelectricity, as well as the thermal expansion, and certainly the piezocaloric effect. Some equation can be extended just by adding other couples of conjugate quantities. For instance, from the mechanical or chemical or even magnetic domain. Obviously, this introduces many other material parameters. With three couples, we have 9 parameters, as listed, namely in this table. With 4 couples of intensive and expensive quantities, we have 16 parameters. So 7 more. For instance, the magneto-caloric effect, expressed as the partial derivative of entropy to magnetic field strength. Okay? A sensor or input transducer performs the conversion of information from the physical domain of the measurand to the electrical domain. Many researchers have tried to build up a consistent classification scheme of sensors encompassing all sensor principles. Such classification of the millions of available sensors would facilitate understanding of their operation and making proper choice. But a useful basis for a categorization is difficult to define. So I can say that there are various possibilities. According to the measurand, according to the application field, according to a port model, according to the conversion principle, according to the energy domain and measurand, and according to the thermodynamic consideration. Today, many books on sensors follow a classification according to the measurand. Why? Because the designer who is interested in a particular quantity to be measured can quickly find an overview of method for that quantity. The most experienced designer may also consult books that deal with just one quantity, for instance, temperature or liquid flow. But much information on sensors can also be found in books focusing on a specific application area. For instance, mobile robots, industrial inspection, buildings, manufacturing, mechatronics, automotive, biomedical, and many, many more. However, an application field provides no restricted set of sensors, since in each field many types of sensors could be applied. And this slide presents a list of physical quantities of measurement. And namely, this list is certainly not exhaustive, but it shows the many possible measurements of quantities. For each of these quantities, one or more measurement principles are available. Okay? The distinguishing property in the classification based on port models is the need for auxiliary energy, as you may see from this slide. Sensors that need no auxiliary energy for their operation are called direct sensors or self-generating sensors. And sensors that need an additional energy source for their operation are called modulating sensors or interrogating sensors. As we back to the first, direct sensors do not require additional energy for convection. Since information transport cannot exist without energy transport, a direct sensor withdraws the output energy directly from the measurement object. As a consequence, the loss of information about the original state of object may be achieved. There even might be energy loss too. For instance, first of all, heat. An important advantage of a direct sensor is its freedom from offset. What it means? It means that at zero input, the output is essentially zero, right? Okay. Examples of direct sensors are the piezoelectric acceleration sensor and thermocouple. Modulating or interrogating sensors use an additional energy source that is modulated by the measurement. The sensor output energy mainly comes from this auxiliary source, and just a fraction of energy is withdrawn from the measurement object. The term modulating and interrogating refer to the fact that the measurement affects a specific material property, which in turn is interrogated by auxiliary quantity. I use too many terms, as you can see in this lecture. But I'm trying to explain a modern scientific level of these variety sensors on our planet. So, most sensors belong to this group. What it means? It means all resistive, capacitive, and inductive sensors are based on a parameter change, like resistance, capacitance, and inductance, okay? And caused by measurement. Likewise, most displacement sensors are of the modulating type. In this case, the displacement of an object modulates optical or acoustic properties. It's maybe like transmission, reflection, and interference, where the light or sound is the interrogating quantity. Do you agree with me? Nice. Let's go. Energy, and thus information, enters or leaves the system through a pair of terminals, making up a port. We distinguish input ports, usually on the left side, and the output ports, usually on the right side. A direct sensor can be described by a two-port model or port-terminal model. Two-port models and terminals. The input port is connected to the measurer, and the output port with the electrical connection of the sensor. Likewise, a modulation sensor can be conceived as a system with three ports, an input port, an output port, and the port through which the auxiliary energy is supplied. You can see here. In this model, the variables are indicated with a cross or a port variable, and through or flow variables, respectively. The subscripts as X, Y, and Z are chosen in accordance with the sensor cue. So the direct sensor provides the information about the measurement as an output signal and energetic quantity. Modulated sensors containing an information as the value of a material property or a geometric quantity, not an energetic signal. Okay? The information enters the system through the input port, where the measurement affects specific material or geometric parameter. To extract the information from such a sensor, it has to be interrogated using an auxiliary signal. In this case, the information stored in the sensor is available latently. In the latent information parameters or LIP. And these parameters are modulated by the input signal and interrogated by the auxiliary or interrogated input. At zero input, the LIPs of a modulating sensor have initial values set by the material and the construction. And generally, the input has only a small effect on this parameter, resulting in a relatively small deviation from the initial value. And you should notice that the direct sensors do have LIPs set by material and construction. They determine the sensitivity and other transfer properties of the sensor. So the input port of both sensors can be denoted as the LIP input port. As a consequence, Any sensor can be described with a three-port model on a figure B. And only the function of the port may differ. Notably, the LAP input port and the interrogating input port. According to the unified transducer model, an input port can be controlled either by design, in this case, it has a fixed value, or by environment. In this case, the measurement of some unwanted input varies. So we have four different cases. Look at this slightly. The characteristics of these four transducer types are briefly reviewed. Design-controlled LIP input and design-controlled interrogated input. All inputs are fixed. And this type represents a signal for information port. For instance, a standard or a signal source with a constant or predetermined output. The output is totally determined by the construction and the material that have been chosen. Do you agree with me? Okay. And any environmental effect on the output is ideally excluded. And design control LIP input and environment control interrogated input. Since the latent information parameters are fixed by design, the output depends only on what is connected to the interrogating input. When this is a measurer, the transducer behaves as a direct sensor. I can give you some examples in this case. It's maybe a thermocouple temperature sensor. In this case, the Seebeck coefficient is fixed by the choice of the material, making up the thermocouple. Another example, piezoelectric accelerometer. In this case, the sensitivity is fixed by the seismic mass and the piezoelectric properties of the crystal. The third example, it's maybe environment-controlled LIP input and design-controlled interrogated input. The measured affects particular materials' properties or geometric parameters. These changes are interrogated by a fixed or well-defined signal at the interrogated input. The transducer behaves as a modulating sensor in this case. And I give you several examples of this. First of all, it's a strain gauge bridge. Very classical explanation. Strain alters the resistance of the strain gauges. A bridge voltage converts this resistance change into output voltage. Don't worry, all of these we will be discussed in later lectures. Another example, second example, it's a linear variable differential transformer. In this case, a displacement of an object connected to the moving core will change the transfer ratio of the differential transformer. An AC signal of the primary coil acts, in this case, as interrogating voltage. The third, very popular nowadays sensor is a Hall sensor. The measurement is, in this case, is a magnetic induction field, which acts on moving charges imposed by fixed or known current applied to the interrogated input. Yes, we will be studying Hall sensors more detailed too. Next example, environment controlled LIP input and environment control interrogating input. In this case, these are multiplying transducers. The output depends on the quantities at both inputs, often in a multiplicative relation. So maybe many each quantity. And for instance, a Hall sensor could act as such when the interrogating input is not a fixed current, according to the design, but a current that is related to just another method. So it will be variable. It is important to know that any practical transducer shows all four types of responses. A strain gauge, a modulated transducer, produces, when interrogating, an output voltage related to the strain-induced change in resistance. But the circuit can also generate spurious voltages caused by capacitive or magnetically induced signals. And a thermocouple, in this case we mean it as a direct transducer, produces an output voltage that is proportional to the measurand as the interrogating input. If, however, the material parameters change due, or maybe for instance, strain or nuclear radiation, inputs at the LIP port, the measurement is a parameter. Since just one response is desired, other responses should be minimized by a proper design. And the universal approach helps to identify such interfering sensitivities. The classification, according to conversion principles, is often used for the reason that the sensor performance is mainly determined by the physics of the underlying principle of operation. But, however, a particular type of sensor might be suitable for a variety of physical quantities and in many different applications. For instance, a magnetic sensor of a particular type could be applied as displacement sensor, a velocity sensor, a tactile sensor, and so on. For all these applications, the performance is limited by the physics of these magnetic sensors. But the limitations manifest in completely different ways. Okay? A closer look at the various conversion effects may lead to the observation that the electrical output of a sensor depends either on a material property, or the geometry, or even a movement. And this table tabulates these three phenomena for various types of sensors. A systematic representation of sensor effects based on energy domain involves a number of aspects. And first of all, the energy domains have to be defined. Second, the energy domains should be allocated to both the sensor input and output. And finally, since many sensors are of the modulating type, the domain of the auxiliary quantity should also be considered. So, from a physical point of view, 9 energy forms can be distinguished. It's electromagnetic radiant energy, gravitational energy, mechanical energy, thermal energy, electrostatic and electromagnetic energy, molecular energy, certainly atomic energy, nuclear, more divided, and mass energy. And this classification is rather impractical for the description of sensors. Line has proposed only 6 domains and adopted the term signal domain. These 6 domains are the radiant, thermal, magnetic, mechanical, chemical, and electric. The number of domains is a rather arbitrary choice. So for practical reasons, we will only continue with the system of 6 domains and call them energy domains. Information contained in each of the 6 domains can be converted to any other domain. And this conversion can be represented on a 6-to-6 matrix. And this table shows the matrix including some of the conversion effects. an input transducer or sensor performs the conversion from a non-electrical to electrical domain. The shaded color, and we have this, the electrical shaded color. And an output transducer or actuator performs the conversion from the electrical to another domain. And we have the shaded row. The cell of the diagonal of the matrix, or you can see here, this one, indicates the effect of within a single domain. Okay? This two-dimensional representation can be extended to three dimensions when the interrogating energy domain is included. And this gives us 216 energy triplets. To get a clear overview of all these possible combinations, they can be represented in a 3D Cartesian space, as you can see in this slide. We call this as a sensor Q. The three-axis refers to the input energy domain and the output energy domain and the interrogating input energy. So on each of these 216 elements of our 6 times 6 times 6 matrix, a conversion effect is located. When restricting to electrical transducers, there are 5 direct input transducers, 5 direct output transducers, and 25 modulating input transducers, and so the same 25 modulating output transducers. So, to facilitate notation, the transducers can indicate it by indices, like the crystallography, so the so-called Miller indices. Miller indices is classical X, Y, and Z, right? So the X index is the input domain. So as we have the index, the priming to the R. The Y index horizontally is the output domain. And the Z vertical index is the domain of the interrogating quantity. With these 3 indices, X, Y, and Z, a transducer can be typified according to the energy domain involved. I might call you some examples as follows. It's maybe direct input transducer, thermocouple, modulating input, Hall sensor, direct output transducer, LED, modulating output transducer, LCD. So these transducers are also visualized in all these figures. The practical value of such a representation is rather limited. It may serve as the basis of the categorization for overviews or as a guide in the process of sensor selection. You know, this lecture deals with uncertainty aspect of measuring systems. And it starts with a review of the most important terms expressing sensor behavior as a tool for making a fair assessment of the system's requirements and performance. And the effect of intrinsic sensor limitations can be reduced by special configuration and procedures. So they are also effective against error caused by the environmental influences and methods to reduce the error due to the sensor deficiencies and instrumentational factors are compensation, feedback, filtering, modulation, and demodulation, and I forgot, and correction. You know, no sensor is perfect. The mechatronic designer must be aware of the sensor's shortcomings in order to be able to properly evaluate measurement results and to make a correct assessment of the system performance. Specify sensor quality in terms of only accuracy is not sufficient. Why? Because a larger number of precisely defined parameters are necessary to fully characterize the sensor behavior. And often, a designer can reduce the effect of the intrinsic sensor's limitation by the application of special configuration, procedures, and even methods. Similar measures can also be considered when environmental influences should be eliminated. And this module reviews the most important terms to express sensor behavior and presents some general design methods. They need to reduce error due to the sensor deficiencies and environmental factors. So, imperfections of a sensor are usually listed in the data sheet provided by the manufacturer. And this sensor specification informs the user about the deviation from the ideal behavior. In this case, the user must accept technical imperfections as long as they do not exceed the specified value. Any measuring instrument, and hence sensor, has to be fully specified with respect to its performance. But unfortunately, many data sheets show lack of clarity and completeness. And gradually, interrogation of agreement about the formal error description are being established. So why we have our discipline, sensor science instrumentation, as a separate part of education, separate engineering application. So an exhaustive description of measurement errors and error terminology, along with an international standard on transducer nomenclature and terminology. Various international committees are working toward a uniform framework to specify sensors. And finally, a special document containing definitions of measurement-related terms is in progress. And first of all, this is the International Vocabulary of Basic and General Terms in Metrology, short VIM, Vocabulary International Metrology. The characteristics that describe the sensor performance can be classified into 4 groups. First, it's a static characteristic, which describing the performance with respect to very slow changes in the measurement. It may be quantity that has to be measured. And in environmental conditions, like temperature affecting the sensitivity or scale factor, offset, and drift. Another group is dynamic characteristics, specifying the sensor response to the fast variation in the measurer, like bandwidth and step response. Third group is environmental characteristics, resulting the sensor performance after or during exposure to specified external conditions, such as pressure, temperature, vibration, shock, and radiation. And fourth group is a reliability characteristic, describing the sensor's life expectancy. So, the errors that are specific for certain sensor types are discussed in course concerns. In this our section, we will define some general specifications, like sensitivity, nonlinearity and hysteresis, resulting accuracy, offset and zero drift, noise, response time, and frequency response. It may be many more, but we define only some general specifications, right? So the sensitivity of a sensor is defined as the ratio between the change in the output value and the change in the input value that causes that output change. Is it okay? Let's go now. Mathematically, the sensitivity is expressed as S is the dy over dx, where x is the input signal or measurement, and y here is the output signal or electrical. Usually, a sensor is also sensitive to changes in quantity other than the intended input quantity, such as the ambient temperature or supply voltage. And these unwelcome sensitivities should be specified as well for a proper interpretation of the measurement result. So to have a better insight in the effect of such unwanted sensitivities, they are often related to the sensitivity of the measurement quantity itself. If the output y is a linear function of the input x, the sensitivity s does not depend on x. But in case of nonlinear transfer function, classical x, y equals f from s, s does depend on the input or output value. And so often, a linear response is prepared to reduce computational burden in, for instance, multi-sensor control system. And in that case, the sensitivity can be expressed with a single parameter. Furthermore, nonlinearity introduces harmonics of the input signal's frequency, and which may obstruct proper frequency analysis of our physical signal. The transfer of a sensor with a slight nonlinearity, you can see as a blue line here, may be approximated by a straight line to specify its sensitivity by just one number. It is blue dark line. The user should be informed about the deviation from the actual transfer. In our case, this is specified by the nonlinearity error. The linearity error of a system is the maximum deviation. Nonlinearity, we can see, so we have maximum deviation based on that. In input or output units, no matter which. Delta x or delta y in this case, or as a fraction, full scale delta x over x. Nonlinearity should always be given together with a specification of a straight line. The following definition finds, first of all, it's terminal nonlinearity. Based on the terminal line, a straight line between 0 to 100% theoretical full-scale point. And second, endpoint nonlinearity. In this case, based on the endpoint line. So the straight line between the calibrated endpoint line of the range. It may be coincide with the terminal theoretical after calibration of zero and scale. May be used so often independent nonlinearity. What it means? In this case, referring to the best fit straight line, our dark line here, according to a specified error criterion. For instance, the line midway between two parallel lines, you have a dotted line in both sides. And enclosing all calibration points. If we have the least square error criterion for the best fit straight line is used, in this case, linearity error is the least square nonlinearity. And we join for this another term, least square nonlinearity. What it means? Based on the least square line, the line of which the sum square of the residual should be minimized. Hysteresis is the maximum difference in output signal with the measured first included. And we see we have the input and output, and we have the maximum hysteresis. We can measure this one. So it's a maximum in hysteresis over specified range, usually over 50%, and then returns to the start line value. The travel range should be specified because hysteresis strongly depends on it. Okay. So next lecture, we will be continuing the same topics. And for now, I hope you enjoyed this lecture, and I'm looking forward to seeing you next time. If you have any questions or propositions, you will leaving me under the video, and we may communicate positively. Goodbye. Hope to see you again.